Jnanam paramam dhyeyam. Knowledge is supreme.
So in the last tutorial we have already seen problems based on particle in a box, and we have calculated the probability density, and we have also seen the bound state energy problems. So now let us get start doing the problems based on probability current density, and few more problems which will give you more flavor of the first part of the tutorial. And here problem 3 is about the finding. So, let PAB be the probability of finding the particle between a range, that is A and B, at a particular time. So, the problem is to show that the derivative of the probability density is equivalent to or equal to the current density at A at time t minus the current density at B at time t, where this is the definition of current density Jx comma t. So, Jx comma t is nothing but the probability current density. So, this is the first part, and the second part is when your so in the first part we have a problem wherein we are finding the probability of the particle in a box. So, we will take the potential to be real. In the second part, the potential is replaced by a complex potential V naught minus I gamma. So, where V naught and gamma are real quantities, and this potential is complex. So, how the probability will get modified, and what will be the rate of probability, and what it will be in terms of this capital gamma. So, let us get started. So, third problem of the first tutorial. So, we write the probability of finding a particle in the range between a less than equal to x less than equal to b is given by, let me call that as PAB. PAB will denote the probability between the range a and b will be given by AB psi star x comma t. So, this is the general expression, and since we have to find out between the two limits, I write it as integral from a to b dp. Now, we have to evaluate this quantity at some t. So, the probability, you take the derivative of probability with respect to time, and since t is independent of x, I can simply take the derivative inside the integral, simple mathematics. So, I can write this as psi star t, and I will use a shorthand notation. I will drop the parentness. This will be, I will have two terms, psi star derivative with respect to t and psi, and the other term would be psi star derivative with respect to psi, and the entire thing times dx. So, this is what we have. Now, we have to rewrite it in the form given to us in the question, which is we have to write this as the probability current density. So, now the next step would be we write the time dependent Schrodinger equation. So, the time dependent Schrodinger equation is given by, so I am using a short form here, time dependent Schrodinger equation will be what? T psi by dou psi by dou t. This is the energy operator which will come with I h cross, which I will take on the right. So, this is my I h cross, this will come on this side, you have a minus sign. This will be nothing but h cross square 2m. Then I have a momentum operator, p square is written like this, plus p of x psi of x. So, this is my time dependent Schrodinger equation. What I do here is I just take the star, that is I take the complex conjugate. So, when I take the star, this minus will become plus. So, I have h cross square, sorry, I h cross minus h cross square upon 2m del square psi by del x square. Now, this wave function will become psi star, and here in this problem in part A the potential is real. So, V of x is equal to V of x star. So, it will remain as V of x and we have a psi star of x. Okay. Now, what we have to do is you have to write this in the form of the current density. So, what was the expression for the current density? It was of this form, psi of x dou psi star by dou t of x plus psi star of x dou psi of x by dou t. You have to evaluate this. So, you consider this part. Okay. So, when you use these two equations, that is you multiply the first equation by a psi star and the second equation by psi, what you obtain is that psi and psi star term for the potential will get cancelled. Okay. So, what I get is I can simplify this as I h cross upon 2m, then I had d square psi by d x square. Okay. So, first term will be with a star and I have a psi of x minus I have d square psi by dx square psi star of x. Okay. This is what I have. So, now what I have to do is I have to do integration by parts, and then after doing integration by parts, what I obtain is just a simple form, that is, let me get back to our expression, which is this expression dp by dt is this. So, I have substituted for these two quantities and I have multiplied the first equation by psi star and the second equation by psi, and I have just added those two equations. So, this would give me simply this expression, there is a integral dx. So, when you do integration by parts, what you obtain is d square, sorry, d psi star by dx. Okay. When I am doing integration by parts, I will obtain d psi of x, okay, minus, I will write here psi star of x. So, I am missing the parentness everywhere. If you write it everywhere, or you can just use a shorthand notation x. Okay. So, this is the form you get when you perform, or rather even before doing integration by parts, you have this form. Okay. And then what you do is you can actually rewrite this as, you have to put the limits of integration. So, the first part, when you put x is equal to b, you obtain a, so there is a minus sign already. So, the first part, when x is equal to b, you obtain j x comma b, minus the lower limit, that is I will have a minus and minus plus. So, that will be x comma a. So, in the end what I get here is, in the end I have dp a b by dt is minus, okay. So, here these steps, this to this requires integration by parts. So, here I have done integration by parts, remember, okay. Once you do the integration by part, you will obtain this expression and then you put the limit and obtain the a part of problem 3, okay. Then what do we do in the next part is, okay, in the b part you are having the potential which is not real, it is imaginary. So, the entire exercise you will repeat from 1 to what we did now, okay, and then what we do is we will have an additional term or additional contribution coming from the imaginary part. So, the imaginary part, so let me write what is given to us. It is given that p of t at p, now a and b are replaced by minus infinity and plus infinity of t is equivalent to, final expression what we obtain in terms of p of t will be of some form in which we have to compare with this expression, okay. So, now the probability is given by probability density, which we calculated in the previous example, was given by, let me write a shorthand notation again, t is equal to a to b, then I had psi star psi, I mean the same expression I will write for psi star v, so I will just rewrite here psi star psi and I have a dx, and then I take the derivative. So, I will have one term plus the second term will be, okay, same way. Again I will repeat the same procedure. I will substitute for the time dependent wave function, using the time dependent wave function I will substitute for these terms, and what I obtain is, I will again obtain the same expression. First part of the expression will remain the same because we have the remaining part of the wave function is the same, the expression is the same, only we have the additional term or the additional contribution coming from the potential. Now, the potential here is, remember, V is nothing but V naught minus I gamma. So, the additional contribution will come from I gamma. So, this V naught and gamma are real. So, I will have an additional term. What is that additional term? Will be, so this step you will have to work out. So, in between psi star dx, okay, and between the limits a to b, let me correct this also, a to b, okay. So, here what we will do is we have obtained the same result plus additional contribution coming from the potential. This you can simply work out, this because of the complex part there will be two contributions. So, I have a 2 gamma h not h cross. Now, what we will do is we will replace a and b by minus infinity and infinity, okay. So, when we replace this by infinity and minus infinity, what do I obtain is dp by dt at minus and plus infinity will be. So, as you all know that at minus infinity and plus infinity, the current density will be 0 because the wave function at x is equal to 0 is 0. So, you will be left with gamma 2 gamma h cross A p psi star psi dx or psi star dx, does not matter. So, now after doing this you can easily write this as, this is dp by dt and you have an integral. So, you can just integrate throughout and obtain h cross times t. Okay. It is very simple and it can be shown, okay, because this you know is nothing but p of t. Okay. So, you have dp by dt minus 2 gamma h cross p of t. So, what we obtain is this expression. So, now you compare this with what is given to us. What is given to us is e raised to minus I t upon tau. Okay. So, now the time dependent wave function, the probability at time t is equal to some t will be given by this for minus infinity to plus infinity, and so you can actually write the relation between gamma. So, what will be gamma? Gamma will be just in terms of tau. If you want to write, what we can do is 2 tau, or tau is nothing but h cross upon 2 gamma. Okay. So, this is what we obtain. Okay. Then we go to the next problem, which says that in the next problem it says that you have a particle which is moving on the surface of a cylinder. Okay. A particle is moving on the surface of a cylinder of length L. So, along the z direction, so z is between 0 and L and r is the radius of the cylinder. Potential energy is given by this. So, for the region between 0 and L, potential is 0, and at the boundary, at the boundaries V of V is infinity. So, you can imagine this or consider this as a particle in a potential well with an infinite potential, same as you have seen one dimensional potential well problem. So, it is very simple to determine the energy eigenvalues and eigenvalues and eigenfunctions. So, the trick will be the same. You start, okay, so here it will be very convenient to use cylindrical coordinates. So, I will be using that. You can use Cartesian coordinates also for a particle moving on a surface of a cylinder of length L, okay, and radius r. Okay. So, we are given this potential well problem wherein V is V of phi comma z is 0 for 0 less than z less than L. So, inside the potential well, the potential is 0 and it is infinity elsewhere. V is 0, V is infinity. So, at these points V is infinity, okay, and this is the radius, this is the length of the cylinder. Now, let us get started. So, we use Cartesian coordinates to write the time independent Schrodinger equation. So, using Cartesian coordinates you can solve this, but I will use cylindrical coordinates. So, we can write the time independent Schrodinger equation in terms of the cylindrical coordinates in this form, okay, minus 1 by z of del square z of z. So, this is a capital Z, this is a small z, z square is equal to 2 in E upon h cross square. Okay. This is the standard form. Now, we are talking about the particle inside the potential. So, V is phi comma z is 0. Okay. So, we do not have the potential term, and this you can write as some A square, and this you can write as some E square. This is an equation with two variables. Let me call this as capital phi to avoid confusion. 1 by r square capital phi. Okay, let me come back here to, so here this was nothing but this is equal to a square. Okay, I am just rewriting this part quickly. Del square capital phi of phi upon phi square. Okay, this is equal to a square. Now, you can easily calculate phi of phi. It is very simple. Okay. So, now this can be written as psi is e raised to I a phi. Okay. And you have a factor of r which is coming from here. So, you will have a r also. Let me write it here. Okay. So, this will be the solution. You have a square r square I into phi. Okay. So, now the next step would be to apply the continuity or the boundary condition. So, at the boundary is equal to phi, this we know, right, at the boundary, that is at after 2 pi rotation phi will be equal to capital phi, okay, which would give us the relation between A and R. So, A will be some L times R. Okay. This again you can just substitute here and you get this expression. So, where L can take any value from 1 to n. Okay. So, this is the relation between L and R. Okay. So, the next step would involve to calculate the second part, that is B part, along the length of the cylinder particle in one dimensional box. I can write the solution simply as 2 by L. Okay. Now, this is the z component, that is the length of the cylinder, is like a one dimensional particle in a box. So, this can be written as n pi b or z by the width, that is L. Okay. Here I have used L. Okay. This is the standard way of representing the particle in a box, the solution for the wave function for a particle in a one dimensional box. Okay. So, now it can be inferred from here that B is nothing but n pi by L. Okay. So, the wave function is given by square root of 2 by L sin B of z, B into z. So, now this final expression is, or the energy eigenvalue is h cross square upon 2m times we have A, which is nothing but, so I will write this as A square plus B square, which we saw will be nothing but E, or h cross square upon 2m is nothing but L square upon R square plus n square pi square L square. Okay. Fine. This is a capital L, this is a small l, remember, is E. So, this is the energy eigenvalue and the wave functions you have seen. And in the fourth, so in the fifth problem, what we do is few steps. I will just illustrate here. So, fifth problem is based on the attractive potential in one dimension. So, the question is, show that that every attractive potential in one dimensional box has at least one bound state with negative energy, and you can prove this using a trial wave function. So, the fifth question you can start by taking now. So, V of x is less than 0 or less than or equal to 0 for all x, and V of x is 0 for some x, right. So, a attractive potential, we mean a piecewise continuous wave function, a piecewise continuous function V of x such that V of x is less than or equal to 0 for all x's, and it is less than 0 for some value of x. Okay. So, now V of x, we know that at x is equal to plus minus infinity vanishes, it will go to 0 for plus minus infinity. So, now let us write down the Hamiltonian operator. H is minus h cross square upon 2m d square by dx square. Now, we are talking about the attractive potential. So, let me put here mod of x, V of x. Okay. So, V is negative. So, I have put a mod sign. So, now if I want to use the trial wave function is alpha upon pi 1 by 4, that is the fourth root, e raised to minus alpha x square by 2. So, now if I operate this on this trial wave function, what do I get? Let us work out this quickly. Simply what we will do here is h on this operator. Okay. So, when you operate the Hamiltonian operator on this wave function, you can see that this wave function has this exponent, and when you operate this Hamiltonian, you will have to differentiate the exponent twice. So, what you obtain is, I will skip the in between step for you to try out, 1 minus alpha x square minus V of x, and I rewrite in terms of psi of x. We have to argue that psi is less than 0. Okay. So, what will be the condition on alpha such that the bound state. So, when I calculate the expectation value, this should give me a bound state energy, that is the negative energy. So, if E is less than 0, so what will be the condition on alpha such that I get the bound state, negative bound state, negative energy, or at least one bound state. So, what I do is I have to actually calculate. Okay. So, again you apply the other end, you apply the wave function. Okay. So, the wave function, when you apply on this, you will get, let me write one more step for you so that you know how to proceed. Okay. So, from minus infinity to infinity, then I have this entire block or this entire expression. Okay. And I have a psi star psi. Okay. So, psi star psi, one part I have already written. So, you will have e raised to, so let me call this as some x. Okay. So, this is some x and then I have e raised to minus alpha x square. Okay. This entire thing would come here, and then you have to perform integration, and once you perform the integration, what you obtain is this expression upon 2m, okay, 2m we have picked up from there, alpha upon pi, okay. And so you will have two parts in this integral. First part I have written the final solution, the second part is nothing but your potential part. You have exponential minus alpha x square dx, okay, from minus infinity to infinity. So now we can see from here that it is the condition on alpha. From here we can see that it is possible to have at least one bound state when alpha, or rather square root of alpha, is less than 4m upon. So, square root of alpha is less than 4m upon h cross square pi in the square root, okay, times this integral, okay, times okay. So, the condition on alpha is that this alpha should be less than this value, that will ensure that we have at least one bound state, that is, this gives us a negative energy value. Okay. These were the 5 problems of the first tutorial. We will be, in this manner we will be discussing the other tutorials also which are in the pipeline. So, after every 4 lectures we will have tutorial based on those lectures. So, see you in the next tutorial.